Good evening, students. We are going to discuss practice paper 14 for 2027 A-level batch. Okay. So in this paper, we have 10 MCQs and one structured essay question. So you can find the structured essay question answers as a PDF. Okay. So I will add that one to your groups. And right now, we are going to discuss the 10 MCQs. Okay. So I will put the answers of the MCQs first. Okay, good. 9 out of 10, 8 out of 10. Okay, look at the first one. The number of electrons with quantum number L equal 1 and Ml equals 0 in bromide ion, Br minus ion respectively. So it is given the atomic number of bromine. Okay, so this is the question. So if you take bromine, its atomic number is 35. So using Aufbau principle and the other related principles for the electronic configuration, we can write the electronic configuration starting from 1s, 2s like that. Okay. So let's try to write that. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. Okay, so I'm writing this one without any hesitation. Why? Because we know that 3D10 is the electronic configuration of zinc. That means zinc is having 30 electrons. Okay, so up to 30 electrons you can write like that. Understood? So the next 5 electrons, okay, so this is basically belong to zinc. So the next 5 electrons, okay, bromine is having 35, no? So next 5 electrons will be there on what? The 4p sub-energy level. So after filling 4s and 3d, then electrons are filled to 4p. Okay. So then it should be 4p5. So this is the configuration of bromine atom. And you can take the electronic configuration in a much easy way also. Okay, how? Because if you take the periodic table, so you can find this bromine and other fellows of the group in the group 70. So starting from fluorine, chlorine, bromine, iodine, they belong to the group 70. Understand? So our fluorine is there in the second energy level. So this one electronic configuration NC 2s2, 2p5. So likewise, fluorine 3s2, 3p5. So in the same way, bromine should end the electronic configuration as 4s2, 4p5. Understand? But in the question, it is asking L equal 1, Ml equal 0. So you can now see we need the full configuration to answer the question. So only the last few electrons are not enough for this question. For some questions you might remember which we already covered in earlier classes, only the last few electron configurations are enough. But for this question, we need the full configuration. And don't forget, it is not asking about what? Bromine. It is asking about what? Bromide ion, Br minus ion. So this is the electronic configuration of bromine. So how should I write Br minus? Br minus means one extra electron is there. So you have to add an electron. So where should you add that electron? Into 4p sub-energy level. So always when anions are formed, electrons are added. So that electron addition would happen to the last sub-energy level. Here it is 4p. So then it would become 4p6, which is a stable noble gas configuration. Understood, Lama? So that's how we write the configuration. So again, I'm repeating this on here, but if it is in the exam, you can just erase this 5 and write 6. Understand? So 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. This is the electronic configuration we need for the question. Okay, we need for the question. Then look at what they are asking. So it's asking how many electrons are there that is having L equals 0, L equals 0 and L equal 1, L equal 1 and Ml equals 0. So what is this L equal 1? So L is the azimuthal quantum number. So there are 4 quantum numbers N, Ml, So N, L, ML, then MS. N represents principal quantum number, which in turn tells you about the main energy level. And the second one, L, the azimuthal quantum number. So it is representing the sort of the sub-energy level. Okay, so whether it is S, P, or D is represented by this L value. Okay, so then ML is there, it is representing the orbitals. So for each sub-energy levels, you have orbitals. Right, for a sub-energy level, you have one orbital. For P, you have three. Like that, we did the discussion several times, right? So ML represents the orbitals. Understand? So then MS represents the spin of the electrons that are residing in those orbitals. Okay, so if you want a more clear idea, you can refer our previous paper classes. It's always already explained in a lengthy way. So today I'm just taking the meaning of L. L represents the sub-energy level. If it is L equals 0, then it is telling you P sub-energy level. So we have to look for the P sub-energy level. We have to look for the how many electrons are there in that P sub-energy level. So now look at that. So here we have 2p6, 3p6, and then we have 4p6. So altogether we have how many electrons? In P sub-energy levels, you have 6, 12, and 18. 18 total electrons. Okay, 18 total electrons are there. Right, that is the L equal 1 electron count. Then you have to see for the electron count that is having ML0. What is this ML0? ML0 represents the orbitals, no? And then if you take this, let's say like this, L and ML values, okay, you might remember this diagram. If L equal 1, sorry, L equals 0, it is S sub-energy level. It is S sub-energy level. If L equals 1, like we saw here, it is P sub-energy level. Then if it is D sub-energy level, it's going to be L equal 2. Okay, so these are the sub-energy levels we have in this configuration. If L is 3, it is F sub-energy level, like that we know. But we need only these 3. And for S sub-energy level, you have one orbital. For P sub-energy level, you have 3 orbitals, while for D sub-energy level, how many you have? You have 5 orbitals. Understand? 5 orbitals. So for each orbital, we have a number. For the S sub-energy level, the single orbital is named as 0. Okay, and here -1, 0, +1. -1 to +1. Here also -2, -1, 0, +1, and +2. So now what we can see, basically in any sub-energy level, you have ML equals 0 orbital, 1 orbital. Understand? So think about that now, right? What did I say now? Any sub-energy level, we have 1 ML0 orbital. 1 ML0 orbital. Okay, so that means in this S orbital, the both electrons are in the ML0 value because they are S now. So you can count these 2 electrons. And here also you can count 2 electrons. Okay, and then from P sub-energy level, you can see in each orbital you can put 2 electrons, right? So here P sub-energy level, you have another 2 electrons. Like that, basically any sub-energy level, you have 2 electrons. In D also, you have 2 electrons here because it is 3D10. And here also 2, here also another 2. So what is the total count? 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2, 16 ML0 electrons. Okay, so your answer should be 18, 16. Answer is answer 4. Okay, can I see a hand raise? How many of you got that answer? The wavelength of a radio wave is 300 meters. Okay, so it's asking energy of 1 mole of photons. Right, so what is the formula? What is the formula? It's a direct substitution. Okay, so we know that electromagnetic waves are actually what? A flow of energy packets. A flow of energy packets. We discussed about electromagnetic radiation as a quick revision. in our recovery class for the newcomers. Okay, so you can access the recording from the group and go through that again. So my point is here, we have an electromagnetic radiation with the wavelength 300 nanometers. So 300 meters. 300 meters. Okay. So it's asking the energy of 1 mole of photon. For the energy of 1 photon, Planck devised the formula E equal h nu. Nu is the frequency. Understood? So then if you want the energy of 1 photon, you have another way of finding it using the wavelength. Okay, so what we are simply doing here, we substitute this frequency using this other formula, C equal nu lambda, frequency times wavelength. Okay, we subject the frequency and put the rest here. Okay, but anyway, that is for the 1 photon. For 1 photon. But here we need the energy of 1 mole of photon. So what should we do? Take this hc over lambda, that is for the 1 photon. So multiply by Avogadro number. Then you will get the energy of 1 mole of photons. Now only substitute and see. Planck constant 6.626 into 10 to the power minus 34 joule seconds. And speed of light 3 into 10 to the power 8 meters per second. And our Avogadro's constant 6.022 into 10 to the power 23 per mole. And then divide this one by lambda. Lambda is 300 meters, so you don't have to change in unit. If it is given in nanometers or something, you can change, but it is not given in nanometers. Okay, right. So now let's try to find out the answer. Now you can see here the 3 and others are cancelling. So I'm going to get the numbers separately. Let's say take 6.6 into 3 into 6 divided by 3. And here the 10 to the power is minus 34, 10 to the power 8, 10 to the power 23, and here you have 10 to the power 2. Simplify this one separately and the numbers separately. Okay, so you have 6.6 into 6 into, okay, so here 10 to the power minus 6, if you cut this one, and 6 plus 23, you have 29. Then 10 to the power minus 5. And the unit is coming from joules, because all other units are getting cancelled. No? Only joules will remain. Meters are getting cancelled, per second are getting cancelled. Okay? And joules per mole is the answer that you will have. So let's multiply 6.6 into 6, 36, 36. 3.96, sorry, 39.6. Okay, so then it's going to be 3.96 into 10 to the power minus 4 joule per mole. But the answer is asking in what? In which unit? In kilojoules per mole. So how do we convert joule per mole into kilojoule per mole? So just remind, how did you convert grams into kilograms? You have to follow the same method. So the meters into kilometers, right? What did you do? You divided by 1000. So here also, what you have to do is divide this number you got by 1000. Then you can get the answer in kilojoules per mole. Okay. So again, you can say, we can say it's approximately, the answer is given like 3.99. There are two answers. I'll put that number 3.99 into 10 to the power minus 4 division 10 to the power 3 kilojoule per mole. So if you simplify this one, it's going to be the answer 3.99 into 10 to the power minus 7. Answer is answer 4. Okay, so can you see 3.99 into 10 to the power minus 4 is also there. That means that is there to confuse you. Actually, we did a similar question. Remember, in 2016 A-level MCQ paper, the very first question they asked came like this. Okay, so usually we are getting the answer in joules, but they asked the answer, they expected the answer in kilojoules. So in that last part, we have to convert joules into kilojoules. So remember that one. Huh? It's a very nice question. Right, so now let's see the question number 3. Okay, so the overall charge here is -3. So it's asking what is the group of A. It's asking what is the group of A. Okay, now look at this one. Right, now just remind the theories about the formal charge for the Lewis structures. That is the point they are checking here. Formal charge of the elements or atoms in a Lewis structure. So how do we get the formal charge? Shall we remind once again? So for example, if I just quickly say that one, this would be negatively charged, this oxygen. Understood? It will be negatively charged. So how did that happen? Because formal charge, we have a formula. Formal charge of an atom in a molecule or ion is given by, okay, number of valence electrons minus number of lone pair electrons minus half of the number of bond pair electrons. Okay, so this is the formula. This is the formula. It was asked to write in 2017 A-level paper. Okay. Yeah. So how do we get the oxygen formal charge? Okay. Let's try for this oxygen. 6 valence electrons in oxygen atom. Okay. So right now around oxygen you can see 3 lone pairs. That means, Lamai, there you have 6 electrons. Okay. So then you have one bond. One bond means 2 electrons. So if you take half of 2, it is 1. So your answer is going to be -1. Understood? That's how the charge will be there. So just remember the formula. Okay. So then each oxygen will have that minus charge. So if you want to understand this further, so if you are not satisfied with the formula, right? If you need more, if you want to go to the root of the logic here, so I recommend this diagram. Okay. So let's take one oxygen A bond. Okay. Now here it is making 4 more bonds, however, right? So if you draw this one once again, you can use this dot cross method. Dot cross method. So each bond is a 2 electrons. So I represented the using crosses, the electrons came from A. Understood? Electrons came from A. Now this is our A atom. In the valence shell of A atom, you have 8 electrons. In the valence shell of oxygen also, you have 8 electrons. So these 2 electrons are shared. Okay, electrons are shared. Now count how many electrons are there, how many dots are there for the oxygen. Okay, oxygen has 7 electrons. 7 electrons, but originally oxygen had only 6 now. Okay, that means oxygen is having 1 extra electron. Because of that 1 extra electron, you will get a -1 charge. Is that clear? That's how it would become -1. Okay, what we do simply when we do questions and all, we just count. Okay, 1, 2, 3, 4, 5, 6, and one of the 2 electrons belong to the oxygen now. So we say just 7. Okay, 7. So one more electron, -1. Very simple, right? Okay, so wait, it is not finished yet, right? But can you see the overall charge is -3? That's the overall charge. So let's say the charge of this X as A as X. Okay. So then the overall charge, this is our overall charge now. Overall charge -3 would be equal to X plus -1 into 4, because there are 4 oxygen atoms. So -3 is equal to X minus 4. What is our X? It's going to be plus 1. Understood? X is going to be plus 1. So now apply the formal charge formula for A. It's very easy. Then you can find out valence electrons of A. Let's say for A, we can find plus 1 is equal to, okay, let's say the valence electrons as, let's say, Y or something. Okay, so Y plus 0, there is no lone pairs. Okay, and half into 8. So there are 4 bonds. 4 bonds means 8 electrons. So 1 equal Y plus 4. Okay, 1 equal Y plus, so not plus, okay, sorry, minus, not, yeah, subtracting it, Y minus 4. So then Y is equal to plus 5. Okay, that is the, so it's having 5 valence electrons. So what's the group with 5 valence electrons? Group 15. Okay, what is the general form, general configuration? NS2, NP5, NP3, sorry, NS2, NP3. Is that clear, Amay? That's how we decide the group number. That's how we decide the group number. This is also an MCQ, came for the A levels, not this exact question. This is a shadow question of that fourth one. In which of the following pairs is the electron pair geometry around the central atom is not the same? Okay, electron pair geometries are not the same. OF2 and H2SE. Okay, just remind water. So how do we draw water? H2O. No? So similar to that, here instead of hydrogen, you have fluorine around oxygen. So there are 2 lone pairs. And H2SCO is also similar to H2S, H2O. H2O, right? It's similar. So then it also must have this arrangement. Okay, so both of them are having basically the same electron pair geometry and same shape also. Here they are not expecting about the shape, but however for this answer, shapes are also same. What is the shape? Angular or bent shape. So we can write something, no? Tetrahedral electron pair geometry. Electron pair geometry. And then you can say the shape is angular or bent. Then look at the next one. Next one is SO4 2 minus and NH3. So by right now, if it is if it is possible for you to figure out the structures without drawing them, if you can imagine the geometry without drawing them, that's very good. Okay. So if you are still not there, keep practicing today. Keep practicing. We'll reach there anyway. Okay. So the structures for these, sulfate is a tetrahedral molecule to iron with sulfate. And NH3 is also a tetrahedral electron pair geometry, but pyramidal shape. So electron pair geometry here is tetrahedral. And this one is having tetrahedral shape. I'm putting shapes in red color. And this one is pyramidal. Okay. Understood. So it's not the answer again. So they are having equal electron pair geometries and shapes. Look at the third one. CO2 and NO2 plus. Remember this one, we draw the same molecules last week also. Right? So they are having linear electron pair geometry and linear shape. Only they have 2 repulsion units. Linear shape also. Remember the bond angle, 180 degrees. Look at the next one. ICl3 and PCl3. ICl3 and PCl. So even though there are 3 chlorine atoms, obviously you can see the central atom belongs to the group 15. Okay, so that means 5 valence electrons. from those 5 valence electrons, if 3 is reserved for bonding, you will have 2 electrons. That means 1 lone pair. Think like that. Okay. So then take iodine. Iodine is in group 17. Group 17. So it would have 7 valence electrons. Out of those 7 valence electrons, if 3 are gone for the bonding with chlorine, you will be left with 4 electrons. 4 electrons means 2 lone pairs. So now you can see around iodine you have 5 repulsion units, but around phosphorus you have 3 repulsion units, 4 repulsion units. So electron pair geometries are going to be different. Is that clear? So that's how you quickly find the answer without drawing in. You are thinking in your head. Can do that, Lama, yeah? Because I know students can do that answers. Some of you are might doing that already. Very good. So anyway, ICl3 is going to be like this. What is this? Geometry, trigonal, bipyramidal electron pair geometry and T-shape. But your PCl3 is having only one lone pair. Something like this, pyramidal. So this is trigonal bipyramidal. This one is tetrahedral. The shapes are going to be, this one is having T shape. This is having a pyramidal shape. Okay, and one last two questions. XeF2 and XeOF2. Okay, now let's see. XeF2, and you have 3 lone pairs. Okay, linear shape, trigonal bipyramidal electron pair geometry. XeOF2, yeah, in this way. That is also a trigonal bipyramidal electron pair geometry and T-shape. Trigonal bipyramidal electron pair geometry. Okay, for the both molecules. What is the shape? Shape is going to be, this one is having linear shape, this one is having T shape. Okay, so your answer is going to be ICA3 and PCA3. So did you understand the way I quickly got that answer? Okay, I thought like this. Phosphorus is there in group 15. So 5 valence electrons. If 3 gone for the bonding with chlorine, okay, 2 electrons remain. That 2 electron exists as 1 lone pair. So around phosphorus, you have 3 bonds and 1 lone pair. So 4 repulsion units. Tetrahedral electron pair geometry and pyramidal shape. Okay, think like that. Then take iodine. Around iodine, if there are 7 electrons, if 3 are gone for the bonding with chlorine, because they share electrons and make covalent bonds. So another 4 will be left. Those 4 electrons are existing as 2 lone pairs. So around iodine, you have 2 lone pairs and 3 bonds. So altogether, you have 5 repulsion units. So the electron pair geometry is going to be trigonal bipyramidal. And when you have 2 lone pairs, the shape is going to be T-shape. Understand that? So like that, quickly think and get to the answer. So don't waste time on drawing them. Just I put them in the board because anyway, it's good for us now to draw more questions. Still at the beginning. Is that clear to you, Lama? Any doubt? Okay, look at this chemical calculation question. What is the mass of Na2SO4 which contains equal amount of sodium ions in 234 grams of sodium chloride? Okay, so from sodium chloride you have 234 grams. Okay, so from this one, find out moles of sodium. Then it is asking what is the mass of sodium sulfate. And go for the moles of sodium sulfate and go for the mass of sodium sulfate. This is what you need to do after breaking the question. So we call it as, the clicking. The question has to be clicked to you. That means you should understand. Okay, this is the way I should move. Okay. So first of all, let's convert these grams into moles. Okay, converting grams into moles. So we need molar mass of NaCl. Sodium 23, chlorine 35.5. You get 58.5 grams per mole. Okay, so now let's find out moles of NaCl. Moles of NaCl. You have 234 grams division 58.5 grams per mole. Okay, so 8.5 you can see it's kind of divisible from 34 now, because 32 is 8 times 4. That's a 0.5 into 4 again 2. So it's divisible, right? So how many you have? You'll exactly have 4. Exactly have 4 moles. Can make sure that after dividing, but anyway, we'll get this answer. So you have sodium chloride 234 moles. So now take this compound sodium chloride. Sodium chloride is actually composed of sodium plus ions and Cl minus ions. So this is like kind of like a reaction. Okay. And then you can see here, if I dissociate or break this one, from 1 mole of sodium chloride compound, I will get 1 mole of sodium ions and 1 mole of Cl minus ions. Okay. So if I had 4 moles here, I should get 4 moles of sodium plus. So now we know moles of sodium plus. Okay, now we came halfway. Now the next thing. So now the sodium is existing as sodium sulfate, no? So if you write it as a compound, you will see there are 2 sodium ions combined with sulfate. So that means I need here 2. So the ratio is 2:1:1. So if you are having 4, it's going to be 4:2:2. So 2 moles. Understand? 2 moles. So 2 moles of sodium sulfate is there. That's our third step, sorry. And then we need the mass of sodium sulfate. So now let's go again and find molar mass of sodium sulfate. Molar mass of sodium sulfate. So sodium 23 times 2, sulfur 32, and oxygen 16 times 4. Okay, 64, 96, 96, 96 and 46. 96 and 46, 12, 142. Okay, so then we can find out the mass of Na2SO4, multiply 2 moles by this 42 grams per mole molar mass. It's going to be 284 grams. 6. Commercial liquid fertilizer is formed by dissolving ammonium sulfate and urea in water. And then it is given 2 reactions. How they are reacting with sodium hydroxide, because once they need to find out the composition of this one, they use sodium hydroxide and did a reaction. You can see the products are sodium sulfate and ammonia and water. Here the products are also given. Urea forms sodium carbonate and ammonia. So for balancing of these chemical equations, we can use inspection method. So here you have to put 2 sodium hydroxide and 2 ammonia. 2 ammonia and how many oxygen you are having? 2, 6, no? So then 2 water. And for this also you can do the same way. 2 sodium hydroxide, sodium sulfate and 2 ammonia. Okay. Right. So it says we needed 50 cubic centimeters of 0.08 sodium hydroxide to completely react with 50 cubic centimeters of this sample. So we have needed how much? 50 cubic centimeters of 0.08 mole per decimeter cube sodium hydroxide solution. Right? So they are asking what is the concentration of urea. If the concentration of this one, the concentration is, they have given it as a data 0.01. If the concentration of ammonium sulfate is 0.01, they are asking the concentration of urea. Okay, so now think about the question. Think about the question, it's not that difficult. First of all, I'll explain the method using symbols. I think that will work better. Let's say we are having X moles of this one and Y moles of this one. Then you will be needing 2x moles of sodium hydroxide to react with ammonium sulfate and again 2y to react with urea. Okay, so the number of moles you are getting here, now this is actually volume and this actually concentration. So using concentration and volume, using N equals Cb formula, remember I reminded you this one last week, you can find out the moles. Okay, so moles of sodium hydroxide is equal to 2x plus 2y. Okay, and then we know the x moles because here we are using 50 cubic centimeters, not from the whole sample. From the whole sample, it is 50. Okay, both solutions are there in the same liquid. So don't forget that. Okay, so using these two data, I can calculate moles of ammonium sulfate. Ammonium sulfate. Understand? So that means X. So we know what is X. So if you know X, and if you know sodium hydroxide total moles, you can find out the moles of Y. That means urea moles. So then from this one, you can get into the urea concentration by dividing Y over 50 into 10 to the power minus 3 decimeter is the volume. That is the method. See, without doing any calculation, I can explain you the method. Moles of ammonium sulfate. Ammonium sulfate moles. So we have the concentration 0.01 and multiply by the volume 50 into 10 to the power minus 3 decimeter cube. So 0.5 into 10 to the power minus 3. That is the number of moles of ammonium sulfate. Okay. So then we can say moles of sodium hydroxide. We can put the symbol M to indicate that moles. Moles of sodium hydroxide reacted with ammonium sulfate. Ammonium sulfate. So since the molar ratio is 1:2, you can say we have to multiply this one by 2. So it's 1 into 10 to the power minus 3. Okay. So then let's write moles of sodium hydroxide added. How many moles are added? So 0.08 moles per decimeter cube. We added total of 50 cubic centimeters. So I turned them into decimeter cube. Okay. So 0.8 into, so 8 into 0.5. So 4 into 10 to the power minus 3 moles. So now you can see out of the total moles, only 1 into 10 to the power minus 3 is reacted with ammonium sulfate. So now we can find moles of NaOH reacted with urea. Or CONH2 twice. Okay. So it has reacted 4 into 10 to the power minus 3 subtract 1 into 10 to the power minus 3. So you get 3 into 10 to the power minus 3 moles have reacted. So since the molar ratio is 1:2 again, we can find out moles of CONH2 twice or urea. Okay, so it will be half of this value. 3 into 10 to the power minus 3 into half. The ratio is 1:2, 1:2. So if you have 2 moles of sodium hydroxide, you will be having 1 mole of ammonium hydroxide, 1 mole of urea. If you have 3 moles of sodium hydroxide, you will have 1.5 moles of urea. Like, so here it is then 1.5 into 10 to the power minus 3 moles. That's the number of moles of urea. So what we need is the concentration of urea. CONH2 twice concentration is equals to this moles over volume. 1.5 into 10 to the power minus 3 moles divided by the volume. What's the volume? 50. 50 into 10 to the power minus 3 decimeter. Okay. So 0.15 division 5 is 0.03 moles per decimeter. Your simplifications will be improved with the time. So can I see how many of you got the third answer? Can I see hand? So 7th one is also a very good question. Just try the same chemical calculation questions we did, okay? In Sinhala we say this is like a titta behetak. It's very bitter, but it's the only way we have to do this calculation lesson. By doing questions, by repeating the same questions we did. Then we get the theory to our head very well. So I also was amazed to see that we had done 14 MCQs on that single topic, right? So I put them as a list. So try those 14 questions and perfectly finish that stoichiometry bridge concept. Right, so here also we have one limiting reactant question and kind of it is a little bit complex. We will see how to get the answer. Okay. Right, so magnesium and N2 react to form Mg3N2. And you can add water to Mg3N2 to form magnesium hydroxide and ammonia. And it is telling that ammonia is reacting with a sample of oxygen, which is kept under certain volume, temperature, and separately 1 mole of magnesium metal is reacted with 0.3 moles of N2. The formed magnesium nitrate, like that, blah, blah, blah. They are telling the thing. Okay, so I'll make a kind of a summary and a map for the question. And it's a good question, yeah? Good question. So don't give up on this one. Just try this question with me once again. Okay, so here we have magnesium metal reacting with N2 gas to form Mg3N2. So let's straight away balance this one. Because anyway we need to balance this. So N2 is there, it's no problem. So for in front of magnesium, I have to put 3. Okay. So that means the ratios are 3:1:1 ratio. And the question is telling that we add 1 mole of magnesium metal. We are adding 1 mole of magnesium metal to react with 0.3 moles of N2. Okay, and the formed magnesium nitrate. So they are asking about this magnesium nitrate. First of all, let's see how many magnesium nitrate is formed. For that, we have this method added and remaining methods. So added moles are 1 and 0.3. Now remember, in this kind of a situation where we are given the moles of 2 reactants, more than 1 reactant, we are not sure about which one is going to finish first. So we need to identify that one by looking at the number of moles. Let's say if you want to completely react this magnesium 1 mole, you have to see whether how many moles of N2 is needed. So if you want to completely finish this N2, you have to see whether how many moles of magnesium you need. So it's all about ratio. Okay. So you have 0.3 moles of N2. So if you had 1 how many moles you need from magnesium? 3. So that means 3 times. So if you have 0.3, how many moles you need? You need again 0.9, 3 times like that. Understand? But we have more than that, no? So that means magnesium they are in excess. So your nitrogen fully will react. Nitrogen will react fully. And here you will be having 0.3. Understood? How did I feel the reactor drop? I checked how many moles of each compound need to react with each other, react completely with each other. Okay, so if you want to react magnesium fully, you need 1/3 of that amount from N2. So that means you need N2 0.33 moles to react with the whole 1 mole of magnesium. But we don't have 0.33, no? We have only 0.30. That is not enough. Okay, so our N2 is the limiting reactant, so it will be fully consumed and there will be no N2 remaining. Here only 0.1 mole will be remaining. 0.3 moles of magnesium nitrate is formed. So the finishing one we call it as limiting reactant. Okay, now the next thing. To the formed magnesium nitrate, it is telling treated with excess water to form magnesium hydroxide and ammonia. Okay, so now this number of moles that was formed from magnesium nitrate, Mg3N2, we are adding water. And it says magnesium hydroxide, then ammonia gas is formed. So let's balance this. To balance this also, we are going to use inspection method. So here we have 3 magnesium. So in front of this, it should become 3. And in front of this, it should become 2. So altogether you have 6 OH and H plus, so 6 water. Understand that? Now tell me, if you had 0.3 moles of this compound, so if it is fully converted into the other side, okay, so you will be having 0.9 moles of magnesium hydroxide and 2 times like that. That means 0.6 moles of ammonia. See the ratio? 1:6:3:2. 0.6 moles of ammonia. Okay, 0.6 moles of ammonia. And that is the ammonia moles we need actually. Okay, and then this ammonia is reacting with what? That O2 moles. O2 moles. So they are telling about the O2 pressure, volume, temperature. So let's find out number of moles of O2. For that, we are using the famous equation PV equal nRT. This was described in earlier sessions. Okay. So PV over RT. 1.2 into 10 to the power 5 Pascal. 16.628 into 10 to the power minus 3 meter cube. And then divide this one by universal gas constant 8.314 joule per mole per Kelvin, and temperature is 400 Kelvin, 127 Celsius. So now divide this one, you have to convert the volume into cubic meters, okay, to get answers properly. So now you can see this also divisible. You have 1 here, you will have 2 here. Here you will have 100 and 0.3. So 0.3 times 2, 0.6 into 10 to the power 10 is also cancelled. So 0.6 moles. 0.6 moles are there. So from O2 also you are adding how many moles? 0.6 moles. Now the question is not finished yet. You can see it's a very big question. Okay, so it's a model question actually prepared by me. So don't worry, these things will not be asked for the MCQs. It's basically like I say, huh? Okay, so that's why I'm telling these 3 questions, they like kind of progress, easy, moderate, and hard. So now just understand where you are. You might be still there at the beginning. Sometimes you might dig this whole question also well. Okay, and whatever the place you are present right now, So you have to take a step forward. Okay. So act accordingly. I gave you some advices. I put some messages to the group. Follow them. Okay. So now let's go to the last part of the question. This NH3 reacts with O2 to form NO gas and water. So we have to balance this. Okay. This is not all. This is not balanced also. Right. So if you put only the hydrogen is not balanced, let's say 3 and 2 in front of this, and then hydrogen is balanced. Okay, so if you put 2 in front of this, oxygen must also added as 2. Okay, so oxygen you have already 2 and 3, 5 oxygen. So 5 over 2. 5 over 2. So we can't keep fractions. No? So therefore multiply the whole thing by 2. So this will become 4, 5. Then this also will become 4. This will become 6. That is the balanced chemical equation. Then use added reacted remaining method, ARR method. ARR method. Added, reacted, and remain. Added, reacted, and remain. It's asking what's the total number of moles of gases remaining. Okay, so now let's add. This one you have 6.6, and from this also you have 0.6. No. And what is the limiting reactant? What do you think? Is it NH3 or is it O2? You can see the stoichiometry of O2 is higher. That means it reacts more. Okay, so when you add equal amounts, O2 must react fully, no? Because it reacts more, 5 stoichiometric coefficient is 5. So the whole 6.6 moles will react. Okay, so reacted moles of NH3. So how do we find that? So from the 0.6, divide that one by 5 and multiply by 4 to find out moles of ammonia react. Divide by the own stoichiometry and multiply by the other one's stoichiometry. I'll remind this ARR one more time in the class. Okay, so don't worry. So divide this one by 5 and multiply by 4. So 0.12 into 4, 0.48. So 0.48 moles has been reacted. So here we'll be having 0.48 moles. And this will be having, are they all gaseous water? Yes. Gaseous water. So you'll be having divide by 5 and multiply by 6. 0.72 moles. So here 0.12 is remaining, here nothing remaining, here 0.48 is remaining, here 0.72 is remaining. So it's asking the total number of gaseous moles. So that means you need to get the sum of these remaining gases. Okay, so 0.12, 0.48, 0.72. So these two will give you 0.6. 0.6 and 0.7, 1.3. Okay, so it's going to be 1.32 moles. That is the remaining total number of moles of gases. 8th question. Out of the following statements, which one or ones are incorrect regarding the atomic spectra? Look at the first one. Emission spectrum of hydrogen can be observed as a set of dark lines presenting bright background. No. Emission spectrum is the other way. It's incorrect, no? A is wrong. Emission spectrum you will observe as colorful lines in dark background. Colorful lines in dark background. So what you observe as dark lines in colorful background is not emission, it is absorption spectrum. So right in front of A, this A is telling you about absorption spectrum. Okay, absorption spectrum. And second one, energy of radiation relevant to the Balmer series is lower than Lyman. That's also true because Lyman is in UV region while Balmer is in visible region. So UV is having obviously higher energy now. So therefore Lyman should have higher energy. Second one is true. Look at the next one. Absorption spectrum is discontinuous spectrum. Yes. Absorption, emission, they all are discontinuous. That means you will see some gaps. In absorption spectrum, you will see dark lines in colorful background. And emission spectrum, you will see colorful lines in dark background. So however, it is not continuous. You will see gaps. Okay. And C is also correct. What about the last one? Lyman series, which is consisted of radiation relevant to transitions of excited electrons that have moved up to higher energy levels, dropping back to the first energy level. Yeah, Lyman series is consist of transitions that are coming to first energy level from higher energy levels. That's true. And but the last part is wrong. No? It is not lies in the visible region. Lyman series fully lies in in UV region. So therefore, the last statement is wrong. The first part of the statement is correct, but the last part that telling it is in the visible region is incorrect. Is that clear? So they're asking the incorrect statements A and D. So answer is going to be answer 4. Yeah, shall we try the next one? Electron pair geometry around the central atom of xenon is Xe of Xe in XeO3. XeO3 is tetrahedral. So we can think and tell the answer also. Xenon is having 8 valence electrons. Oxygen usually make double bonds. So it takes 2 electrons per 1 oxygen. So if you have 3 oxygen atoms, it will take 6 electrons from the 8 total valence electrons of xenon. So there will be 1 lone pair left. Okay, so that means it is correct. Electron pair geometry is diagonal plane. So tetrahedral. The molecule is XeO3. Okay, so this is the simple structure. You can straight away take that. Remember last week I teach you a short method. You can follow that. So xenon is in group 18. It is a noble gas. So it has 8 valence electrons. Out of that 8 valence electrons, oxygen is making double bonds. Okay, and then 6 is gone. So 2 electrons are there. That 2 electrons are existing as one lone pair. One lone pair. Okay, so around xenon you can see 4 repulsion units are there because we count, remember, we count multiple bond as one repulsion unit. Here you have 4 repulsion units, 4 VSC PR units. That's why it was tetrahedral, okay? That's why it was tetrahedral electron pair geometry. So if the first statement is true, you have to look for a reason because sometimes the second one is also correct, right? So my reason is it was tetrahedral electron pair geometry because it has 4 repulsion units. Okay, now let's see what is the second statement is telling. It tells there are 4 VSCPR units around the yes. So then it explains also. Correct and explain. Answer 1. Okay, so look for an earlier paper to see the combinations. If the first one and second one both are correct, and the second one can explain the first one, we'll choose the answer 1. If the second one is correct, but if it cannot explain the first one, we select the answer 2. Okay, so here it is answer 1. Right, so the last question. Hybrid orbitals in a particular atom can overlap linearly or laterally with a hybrid orbital or unhybridized atomic orbital of another atom to form bonds. Okay, Laman. So type and tell me why the last statement is wrong. I got one answer. Yeah, telling lateral. Very good. Telling lateral. Lateral is incorrect, no? Because hybrid orbitals can't overlap laterally. So they only make what overlap is? Linear overlappings to form sigma bonds. They don't laterally overlap. So if laterally overlap, let's say p orbital or something, d orbital will make lateral overlappings make 5 bonds. Okay, so our what is this? Hybrid orbitals can't make 5 bonds. Another one is telling since lateral overlapping does not occur for the hybrid orbital. Very good. That's why the first statement is wrong. So if you want, you can put some diagram also to explain. It's for the 9th MCQ, it's for the 10th MCQ. So these are the hybrid orbitals. Hybrid orbital. So if hybrid orbitals are overlapping linearly with another hybrid orbital or linearly with an atomic orbital, it can happen like this. So this is let's say sp3 overlap. sp3 1s overlap. sp3 2p overlap. Like that, they linearly overlap. They never overlap laterally. Can't happen. So basically resemble the same thing. So laterally overlapping can happen if the electron densities are symmetrical and if they are in either sides. Here, this is the lateral overlapping of p orbitals. So the first statement is incorrect. Look at the second statement. Linear and lateral overlappings of orbitals result sigma and pi bonds respectively. That's true. Linear overlappings give rise to sigma and lateral overlappings are giving rise to pi. That's correct. But anyway, the first one was wrong. So answer is answer 4. So right. So thank you for staying. Goodbye, Lamai. Study well and show the papers and reviews next day.